Okay, why don't we get started? Quiet, please. Okay, greetings and welcome to lecture 9 of the computer vision model. Today you're in for a real treat. We're going to talk about video and emotion. So just a quick recap from last week. Last week we talked about 3D vision, and in particular we looked at stereopsis, which is where you have multiple cameras that are imaging the scene. You want to understand the scene from those multiple views. So very fundamental to stereopsis is matching. So you want to find correspondences or points that refer to the same 3D location in 2D images. And if you can do that, you can compute disparity, which is related to depth. We also took a look at the fundamental matrix, which is a very useful matrix which helps encode the epipolar geometry of the multiple views. And it allows you to reduce the search for correspondence along a one-dimensional line. And we also talked about how to estimate the fundamental matrix, and a really good technique for that is called ransack, which allows you to fit a simple model in the presence of outliers. We also took a look at camera calibration, so we talked about extrinsic camera matrix. You're already familiar with the intrinsic camera matrix. And when you put the two of those together, you have a projection matrix, which allows you to project 3D points into a 2D image. And we even worked out some of the mathematics on the board. Once you can do that, you can then project 3D surfaces into 2D images, and we did some augmented reality. And then I covered structure for motion, where you have a video sequence and you reconstruct 3D points in the scene as well as the camera geometry. Okay, so today we're going to cover video, and we're going to see how in MATLAB you can very easily load a video, and then you can manipulate individual frames. And in fact, you can also then save a video with just some very simple lines of code. Once we can load a video, then we're going to analyze it as computer scientists, computer vision scientists. We're going to take a look at motion detection, and we'll talk about optical flow, which describes how pixels are moving in video sequence. Then we'll talk about tracking, and in particular, we're going to look at the KLT tracker. It's a very good way to track points through a video sequence. I'm also going to save a little time at the end of today's lecture for module evaluation feedback. So we got some forms here, and we'll save maybe 5 to 10 minutes at the end for you to fill out the form. Okay, so last week we started talking about 3D, and in fact, you can think of video as 3D as well. In fact, in video, you basically have 2 dimensions, x and y, which correspond to the spatial axes. But now you're adding a 3rd dimension, which is time. Okay, and the time corresponds to the various frames that are in the sequence. So maybe my first frame is down here, the person's kicking the football, and as we go through time, there's some motion that's happening in the sequence. So if you think about it in mathematical terms, what we're doing essentially is adding a 3rd dimension corresponding to time. So this lecture kind of feeds very naturally off of last week's lecture when we were talking about 3D. In that case, it was purely spatial. Now we have a temporal variable. Okay, so when you come to video, one of the important characteristics you want to think about is the frame rate. And that is usually described in hertz or frames per second. It means the same thing. And essentially that's describing how many frames you're getting every second. So if you watch a traditional film, it's actually at 24 hertz, 24 frames per second. If you're watching PAL television, it's at 25 hertz. Most high-end TVs these days are doing 50 or 60 hertz. And in fact, I think many of you have your laptops open. Your laptop screen is also refreshing at 60 hertz. That's a very common frequency. And in fact, 60 hertz is supported by YouTube, and most cameras and video equipment are going to record at that rate as well. So at that relatively high frame rate, you don't see much flicker. So if the frame rate gets too low, the video looks juddery, it doesn't look very nice. So you want a good frame rate. 60 hertz is great. In fact, you can even go higher, okay? There are special cameras that allow you to record at a very high frame rate. And you know, you can do some really interesting things. If you click on this link later, you can watch a video of the slow-mo guys. Maybe some of you have seen the slow-mo guys before. They have slow-motion cameras, and here they've got some paint that's moving based on music. And it's at a very high frame rate, so when you slow it down, you can see the motion very precisely. It's super interesting. Okay, so if we want to use videos in MATLAB, we need to load them and get access to the pixels that are on the frames. So the first thing you might want to do is just even play a video. And for that, you can use this function called implay. It's super easy. You just call it with the name of your file, okay? And in MATLAB, you can have an AVI file that's very standard format, especially in Windows. There's also MP4, so MATLAB will load these things for you. And you know, you can just play the video back. So that's cool. But you know, we're computer vision scientists. We want to actually analyze the video. And for that, we need to load it up into memory and then access the individual frames. So for that, there's this other object called a video reader, okay? And with the video reader, you can load up your video and then you can get those frames. So here's an example where we first create a video reader object, and we're going to pass in the name of the video we want to load. Then we're going to just have this while loop, and while there's another frame to be accessed in the video, we're going to grab it, okay, with this read frame call. That will give you the image on the current frame, and then you can display it, okay? Now, if you want to, you can use imshow to show the image, but turns out imshow is a little slow. If you want to play a video at high frame rate, it's better to use this thing called image, okay? So you just pass in image and with the variable representing the image, and then you can play that video back, and you can even pause it based on the frame rate so that it plays back at the appropriate frame rate. Does that make sense? So this gives you a very convenient way to load a video. And here you'll see we now have access to the individual frames that are in the video clip itself. Okay, well, if you can read a video, you might want to write a video. And that's not hard. Not surprisingly, there's a video writer object, okay? So you can create one of these. And here what I'm going to do in this example is I'm going to take every individual frame from the video and I'm going to invert its colors, okay? So what I'm going to do is I'm going to create a video writer where I can save the negative of the video, and I'm going to encode it using an MPEG-4 encoding. So once I've created that object, then I'm going to open the file for writing. And then all this code is very similar to the code we just saw in the previous slide. Okay? The differences are highlighted in yellow. So here I'm going to write to the video file after I've inverted the color. Okay? And that's about it. And then when I'm done, I can close the file so that you can tell MATLAB I've done writing to this file, and then it will be accessible to you in the operating system. Does that make sense? So this is a super easy way to read and write videos, and you know, MATLAB just makes it very convenient. Okay, there's this other thing called a video file reader, okay, and it's part of the computer vision system toolbox. So it's kind of similar to the one before that we saw. I guess the main difference here is that you use this step function instead when you want to grab a frame. Okay? So here we've got a video file reader. Okay, we're going to load this MP4 file. This is one of the examples that comes with MATLAB, actually. So we're going to create the video reader. To grab a frame, we call it step function, and then we can show it. And here, kind of a similar construction, we're going to have a while loop, and we're going to just loop over all the available frames that are in the video. But here you're going to check to see if the video reader has any more frames, so you call is done. So we're saying if we're not done, then grab the next frame and then display it. So you see there's actually two ways to load videos. You can pick whatever one's convenient for you. This one's part of the computer vision system toolbox. Okay, so once you're able to load videos and get those frames, you're now ready to do computer vision on videos. And in video analysis, there's like a load of things you can do. Okay? If you look at the computer vision literature, you'll see loads and loads of papers doing different types of problems. So one classic problem is motion estimation. So first you might want to know if there's any motion at all. And then if so, where is it in the image? And maybe you also want to know where the pixels are moving. Okay? We're going to cover those topics today in this lecture. Another very common problem is tracking. Okay, so here we're tracking pedestrians in an urban environment. So maybe you're going to detect people, you're going to follow them through the video sequence to see where they're going. And here you can imagine there's lots of challenging problems with occlusion, where maybe some pedestrians are blocking the view of other pedestrians, and dealing with noise and other challenges. Another very common problem is super resolution, and here you can think of it in terms of spatial or temporal variables. This is an example of spatial super resolution. So the idea here is you get a video sequence of an object, but that video sequence is at low resolution. But if you can kind of combine all the frames, all the information that's in all those frames, you can actually super resolve to get higher resolution detail. So here we can see this license plate quite clearly, but on the individual frames, it's quite hard to see the characters precisely. Yet another example is structure for motion. In fact, we looked at that last week, right? So we had a video sequence, and then we analyzed the video by tracking points, and then reconstructing them in 3D along with the camera locations. So there's loads you can do with video. It's a super interesting domain. And today what we're going to do is take a look at motion, and see how we can determine if pixels are changing, if so, where they're moving, and how to implement some tracking algorithms. Okay, so the first thing I want to talk about today is background subtraction. Here, what you want to know is if there's change in the video. For example, maybe you've got a surveillance system, okay? You've got this camera that's looking at the road. You want to know if there's a car coming down the road. So one way to do that is to look at change. So you can take, say, a background image, okay, before there's any cars in the field of view. And then on the current image, you can simply just subtract these two. You get a difference image. And then you can look at where the differences are, okay, in the result. And so this is actually a really simple way to essentially subtract the background and see what has changed. So mathematically, it's really simple. We're going to take the current image, we're going to subtract off the background, okay? And we can do that at every frame t. And if the difference is above some threshold, then we say that pixels should be on. It's in this mask, so those are the white pixels. And then otherwise it's 0, so the pixel hasn't changed color essentially. And with that, we can actually determine which pixels are changing in the video. Yeah?
You can have like a time-based data set of backgrounds in the situation.
Yeah, this is a great question. So there are some flaws with this approach. Obviously, what happens when the sun goes down, right? I mean, that's not going to work anymore. The background has changed. So yeah, you could absolutely have like a database of background images. And in fact, you could even try to compute the background adaptively. I'm going to talk about that in just a minute. It's a very good observation. If I want to implement this simple algorithm in code, it's not too hard, okay? I can load the current frame. I've got the background as another image, okay? And here I'm just going to look at the difference between those two images. And these images are colored, right? So I've got red, green, blue channels. So this is just looking for the maximum value across red, green, and blue. And then anything above some threshold I'm identifying as moving or changing. So, well, you anticipated my question. What are some limitations of this approach? Okay, one limitation is the background, the might actually change, like time of day. Like during day, the background might look very different to nighttime. Do you see any other limitations to this approach? What else could go wrong with this?
What if the object is fairly similar to the background?
Yeah, exactly. So what if the foreground is very similar to the background? Then you can have some problems. This threshold might not work. And indeed, there are lots of challenges here. The background could be moving. Maybe the wind is blowing, and you've got shadows that are cast. And those shadows are, kind of shifting in space. So, there's a lot of things that you might want to do. Even here in this image, you can see there's a lot of clutter. Okay, this clutter up here is actually coming from trees. So if we go back, you see there's trees and shadows up here that are causing some pixels. Probably the wind was blowing, and this threshold isn't working with the wind. Okay, but we can, of course, do some post-processing. So if you have like a binary image like this, okay, hopefully after lab 5 on segmentation, you're able to manipulate the image and remove some of these kind of floating pixels. Here I'm using the BW label command and just finding the largest connected component and keeping that. Everything else gets set to 0, and it's a very simple way to filter out all of these floating pixels. Okay, so the simple technique, it might work in some scenarios, but you can imagine if we want to make it more robust, we probably need a little more machinery behind this. And really a good way to deal with that is to try to improve the background model. So how do we get a better background model? Well, one thing you can do is instead of having a static image, you can actually compute some sort of average or median over the last n frames. And n can be fairly large. This will allow the background to adapt. Okay, so as time goes on, maybe the light is getting darker, or it's getting brighter. You'll be able to update that background model as you go. As long as foreground objects are moving quickly enough, they won't get caught up in the background. So here's a very simple way. We're just going to have some sort of moving average through time, okay, where we're going to just average all of the last n frames, and that can be my background model for the current frame. If you want to take it further, what you can do actually is have something like this for every pixel in the image. So at each pixel, you can compute like a Gaussian model. So you have like a mean represented by mu and a standard deviation sigma. And you can base those on the last n frames. Then if the pixel on the current frame is not fitting the background model, then you can classify it as foreground pixel. And that way you can find the pixels that have changed. And indeed, there are even fast ways to incrementally update the mean and standard deviation. So, there's ways to make this super fast and practical. Okay, so in the MATLAB computer vision system toolbox, there is a vision foreground detector which embodies some of these principles. So this thing is a system object, and it's going to detect foreground pixels for you for a stationary camera. And it uses this Gaussian model, but instead of having one Gaussian model for every pixel, it allows more than that. You have 2, 3, even 5 different Gaussian models at a pixel. All of them are trying to represent the background. So what it's doing is it's updating this background model on every frame, and it checks to see if the current pixel is matching the model or not. If it matches the model, then it's a background pixel. If it doesn't match the background model, then it's considered a foreground pixel. And this thing allows you to adjust the learning rate so that you can update the background model more quickly or more slowly. So here's an example. I'm going to load up this file. This comes with MATLAB, so later you can copy paste this code into MATLAB and give it a try. So I'm loading the video, and then I'm going to use this foreground detector, and I'm going to initially train it to fit this Gaussian model with 5 frames. okay? And I'm also going to use a blob analysis. And what this is going to do, it's going to require a minimum blob area of 250 pixels. So a blob is just a collection of pixels that are connected to each other. Okay? So this will filter out all of those spurious pixels that we saw earlier using a very similar technique based on connected components. The other thing this code is doing, it's inserting a shape. Okay, so if once I find something to track, I'm going to put a box around it. And here's the code. So I've got a loop. Okay, I'm going to loop over all the frames in my video. And for each frame, I'm going to step the video reader. It's going to give me the current frame. Then I'm going to step this detector, okay? And it's going to give me the pixels that it thinks are in the foreground. And then I'm going to step the blob detector to only retain the blobs that have at least 250 pixels that are connected to each other. Once I've done all that stuff, now I've got the blobs that are representing the moving objects. And here I'm just going to draw a rectangle around them and then show the result. So that's what you see here. And maybe later you can give this a try. And in fact, there's a lab tonight, by the way. So I made a lab, and you're going to get to do something just like this in today's lab if you want to. Any questions about that? Okay, let's move on. So you can detect if pixels are changing, okay, and you can detect where they're changing. But what all of that doesn't do is tell you where the pixels are moving, okay? You don't know what direction they're going, where maybe that's something of interest. And in fact, in the optical flow problem, what you want to do is have a very precise description of where those pixels are moving in terms of their direction, as well as their magnitude. So how fast are they going? So here we're getting into velocity, okay? We want to know the velocity of every pixel in the image. So optical flow is actually defined as the motion observed in the video resulting from relative motion between the camera and the scene. And what we're going to end up with is a vector field. Okay, and a vector field is just essentially a collection of vectors. Every pixel where we compute optical flow, we're going to get a vector. It's going to tell us where that pixel is going on the next frame. So here's an example. Actually, this is a sculpture in Ann Arbor, Michigan, where I'm from, actually. I used to push this sculpture all the time. And when you push it, it rotates, okay? And when it's rotating, the parts that are moving over here are moving very fast because they're farther away from the center of the axis of rotation, whereas these points are moving more slowly, okay? So if you capture a video sequence of this thing rotating, and then you compute optical flow on it, maybe you'll get something like this, okay? Here's a visualization. It's a little hard to see, but these are actually arrows, okay? Maybe some people in the front can see there's like, kind of a line and then a head on the arrow. And it's basically saying where each of these pixels in the image are going to move to on the next frame. Does that make sense? Okay, so the task here is to compute that vector field given a video sequence. So we want to compute this optical flow, but in order to do that, we need to make some assumptions. And the one standard assumption is brightness consistency. So in the brightness consistency assumption, or constancy assumption, what you're assuming is that the brightness of a pixel isn't going to change. You're going to be able to find it somewhere else in the image. So here's an example. At the top of this football, okay, I've got this kind of white pixel, okay, and I've drawn it with an orange dot. I can find that same pixel on the next frame. It's over here, okay? So its location has changed, but the brightness is preserved. It's just in a different part of the image, okay? So what we're assuming is that this pixel, xy, okay, it's going to move to a new location. I'm going to call that x plus u, y plus v. And if I want to, I can represent u and v here with this vector, okay? This is the optical flow vector for this pixel. So basically it's telling me where this pixel is going to go into the next frame. Now, in fact, you can think of u and v as a velocity vector. Okay? So this is telling you where that pixel's going to go. It's got a direction and it's got a length. Okay, its length is the speed, so how fast it's moving, and the direction, encodes which way it's going to move. So if we make this brightness constancy assumption, what we can say mathematically is that this point, xy, okay, has a brightness. I'm going to call that I of xy, and the current frame is t. Okay, so this pixel or this frame has a certain brightness, and what I'm going to say is that with brightness constancy, that same pixel, that same brightness, it exists somewhere else in the next frame. That location is I of x plus u, y plus v, t plus 1. Okay, so t plus 1 is giving me the next frame. Okay, so my frames are arranged temporally. And then, I'm just going to move displacement uv along x and y, and I'm going to go find that point. Does that make sense? So with the brightness constancy assumption, we can write this equation, and now we can do some mathematics. So here we're going to do a Taylor series expansion. So we're going to assume that the motion is small. Okay? And if we do that, then we can write the motion like this. So here's the intensity at the current pixel location and time. And then I'm going to take a derivative with respect to x, and I get multiply that with u. I take a derivative with respect to y, and I multiply that with v. Then I have a derivative with respect to t. Okay? So this is a very standard Taylor series expansion. Hopefully you've seen this thing before. And if you look closely, there are some things that are hopefully familiar to you, having done image filtering a couple of weeks ago. So the first thing hopefully you see is that there's a derivative di dx. Okay? That's the derivative with respect to the horizontal spatial coordinate. Okay? Basically, it's the image derivative in x. Same thing in y. Okay, now we have derivative corresponding change in brightness as a function of vertical axis. And here is the image derivative in time. So in fact, you've seen di dx and di dy before. That's just the gradient of the image, right? Okay, so anyways, if we want to rewrite this, we can say, the change in brightness equals this equation. Okay, so I'm just taking this and I'm bringing it over to the left side of the equation. And if we assume the brightness constancy assumption, okay, then actually the brightness hasn't changed when I compensate for the motion. Okay, just like we said before, we know where those pixels are moving based on u and v. So these two brightnesses should be the same because I've got that same brightness somewhere else in the next frame. So if we do that, then this term on the left side, it's actually 0. Okay, I've made that assumption that they're 0. And now I've got all of the terms that are on the right side of this equation. And if I want to get fancy and rewrite this using vector notation, it looks like this. So I've got the gradient of the image, okay, that's di dx and di dy. And now I'm doing a dot product with u and v, okay, this is my motion. And that equals negative di dt. Are you with me on this? So this is known as the optical flow constraint equation. And it gives us a way to constrain the changes in the image relative to the gradient and the motion and the brightness as a function of time. Yeah. The thing is, though, is this equation sufficient to recover the image motion? And the answer is no, because we have one equation, okay, but we have two unknowns. The goal here is to estimate u and v. So we're kind of in trouble because although this equation gets us part of the way there, we don't have a way to actually solve for the optical flow based on this equation alone. In fact, the component of the motion parallel to the gradient can't be computed this way. And in fact, we get into something known as the aperture problem. I think maybe Slabaugh covered this back in lecture 1. I'm just going to review it again briefly. So in the aperture problem, you've got a scenario kind of like this, where I've got this blue line, okay, and it's going to move. So it's moving through time, okay? And if you look at the blue line, it's actually moving kind of in a downward to the right direction, okay? You see that? But if you only look in the circle, okay, so this is the same example, I'm just removing everything outside of the circle. Now which way is it going? Up. So we're perceiving it as going up and to the right, even though the object actually is going down into the right. So the aperture problem can be a little tricky. So in order to handle the aperture problem, what we need is an additional constraint. And there are different types of constraints we can bring in, and this will bring us to different algorithms for computing optical flow. The first one, we're going to assume that the optical flow field is smooth, which means it's not changing radically from pixel to pixel, okay? And if we make that assumption, then we have a second constraint where we can now solve for the optical flow field. And in this Horn-Schunck method, they actually formulate the optical flow estimation in terms of partial differential equations. So here I have an energy that I want to minimize, okay? And the goal is to find the U and V that minimize this energy. Now the energy has two terms. The first term is based on the brightness constancy assumption, okay? And we just covered this. Actually, this term should be 0, because if we make the brightness constancy assumption, we get the optical flow constraint. And optical flow constraint says this term should be 0. So if we have good optical flow that matches our assumptions, then we want to find a flow field that makes this 0. And in the Horn-Schunck technique, the other thing they're doing is making sure that the flow field is smooth. So what we're going to do here is take derivatives of the flow with regards to x and y, okay? Since I have flow horizontal and vertical, I end up with 4 terms here. And here what I'm doing is I'm penalizing flow vectors that change. Okay, so I want kind of smoothly varying flow vectors. And so if I put these 2 terms together, I can actually solve for a flow field. And actually, you can derive it. It's a little long, I have to admit, so I'm not going to go into the details here. But if you click on this link, you can check out the derivation, especially if you like the PDEs, partial differential equations. You can read all about it. Okay, any questions about that? Yeah.
Sorry, you used some time with the previous equation
Yeah. That's right. So the previous equation, actually, it's encoded in this green box. So if I go back, essentially we've got this term, which should be 0. And so you see that here, it's the first term. So they're used in conjunction. So we've got the optical flow constraint here, and then here's the smoothness property. Okay, so if you want to do this in MATLAB, it makes it super easy for you. You don't have to solve partial differential equations by yourself. MATLAB has already done it for you. All you have to do is call this estimate flow function using an optical flow HS object. So HS stands for Horn-Schunck. These are the guys who invented this approach. So here's how you might use it. So you can call this estimate flow function. You pass in the current image, and you have this object. Object is an optical flow object. And you can create that with this optical flow HS function. And here you can even pass in some of the optional arguments, like how smooth should the optical flow be. This technique's iterative, so how many iterations do you want to do, etc. And here's some code you see on the bottom of the screen, which is creating an optical flow HS object. and then it's grabbing each frame of video, and then it's estimating the flow, and then it's actually visualizing the flow on top of the moving pixels. So let me see if I can run this. Got my MATLAB here. Oops. All right, how cool is that? It's really fast. You saw it ran in real time. I do have a nice computer, but still, it's running really fast. Okay. So it's super easy to compute optical flow in MATLAB. Any questions about that one? Yeah.
Well, is the, I mean, is it dependent on how fast the object's moving in terms of how much you can keep track of it? So if it's moving, obviously, with that you've got cars, but
It gets harder when objects are moving very quickly, and especially if you have motion blur or these kind of things, they start violating this brightness constancy assumption. So yeah, you get better results when the motion is slow, and there's no motion blur. But you can control some of the parameters in this, like the number of iterations, might give you a better estimate if there's faster motion. But
and if you've got something which is obviously moving very fast, but you can keep track of it, does that mean you can keep track of everything as fast as that and slower? So in other words, you've got
Yeah,
a
that's right.
range in terms of anything else.
Yeah, so you should be able to track slower things, using this technique. That's true. Okay, here's an example of kind of playing around with some of the parameters. So here I'm adjusting the smoothness, kind of increasing it, and you see these flow vectors, maybe they are more spatially cohesive. Here, changing the number of iterations in the algorithm, maybe we get larger flow vectors, etc. Now, if you look at this carefully, it's not super precise, okay? It is finding the pixels that are moving, and it is giving you an indication of where they're going. But, like here, for example, you've got these flow vectors that are pointing this way, right? But this car is moving this way instead. So, optical flow field is not perfect, but it's pretty good, and you can do a lot of really cool things with optical flow. Now, I want to explain another way to do optical flow. And this one is called Lucas Canade, after the computer vision scientists who invented it. And essentially here, we're also going to assume spatial coherence, just like Horn and Schunk. But the difference here is that we're going to assume that the flow vectors are the same in a small patch. Okay, so I might have a current pixel. I'm going to look in a patch around that pixel, and I'm going to assume that the flow vectors are all the same in that patch. So for example, let's say I have a 5x5 patch, okay? Then I can get 25 equations based on the optical flow constraint. And I can write them out like this, okay? So at pixel 1, here's the optical flow constraint equation, okay? Then I can do the same thing at pixel 2, and so on, until I get to, n of these pixels. 25 in this case, if I have a 5x5 patch. So, this gives you actually an overdetermined set of equations. Okay, we're only trying to solve for u and v at the current pixel, so I have 2 unknowns. But now I have 25 equations. Okay? So that's actually a good thing to have. We've got an overdetermined system. How do you think we're going to solve this overdetermined system for u and v? What do you think? Any ideas? Least squares, yes. So least squares is a great solution for solving linear equations when you have overdetermined system. And here we're just going to write it in matrix form. Okay, so I've got Ix, it's going to be multiplied by u, plus Iy multiplied by v, equals negative It for that pixel. Okay, and I'm going to do that for all the pixels that are in my 5x5 patch. So if you look at this carefully, you can call this matrix A, okay, and it's n by 2. And then this is just a 2 by 1 vector, okay, and then this one is n by 1. And we can solve this using least squares, using the pseudo inverse. I think you've seen this before. In fact, we did something similar last week. And it's really easy, okay, so you can construct these matrices and then solve. And then you get the displacement u and v. which tells you where this pixel is moving to the next frame. Does that make sense? Okay, so if you want to do this technique in MATLAB, it's also super easy. In fact, it's nearly identical to the one we just looked at. Here, though, we're going to use an optical flow LK object. And what we're going to do is create this object and then just pop it in to this estimate flow function. So now estimate flow is going to use an optical flow LK object, and we can get the flow that way. So let me run this one for you. It's actually kind of similar to the last one, but hey, let's do it. Okay, so also super fast, running in real time. Okay, any questions about that one? Yeah.
Seems like when the images and slides emulate the space that is occupied around each moving object is quite a bit larger.
Yeah, that's right. So that's partially due to the visualization, but because I'm drawing the vectors kind of on a grid. But also, yeah, I mean, the vectors, some of them are pointing like kind of in the wrong direction. So, it kind of makes the object look kind of elongated. Even here, there's kind of a lot of weird vectors going on, mainly because there's a shadow in front of the car. So, this optical flow, it's good, but it's not perfect, I guess is how I would describe it. Yeah?
In that situation, you were saying that obviously you've got an object moving from one brightness spot to the same brightness spot. Obviously, there's in a white area like that.
Yeah.
There's a number of possibilities that could make.
Absolutely. Yeah, that's a great point. So, so here, there's actually a correspondence problem. Like, how do you find, if you have like a white pixel on the previous frame, and there's a whole bunch of white pixels on the next frame, where's the correspondence, right? At the end of the day, we're solving a correspondence problem, just like we were before. And it's ambiguous, okay? Matching one white pixel to just a whole bunch of white pixels in a similar area, it becomes very difficult to match at a very fine level. So, there are other ways to deal with that. In fact, you can compute optical flow in a hierarchy. So you start off with kind of a low resolution image. You compute the optical flow field that way, and you project down into a higher resolution image, re-estimate the optical flow, like kind of refine it, and then go down. So that way you can kind of fill in, like in these places where maybe it's very ambiguous on a very coarse resolution. Actually, you could maybe say that all of these points are moving in the same direction. So a hierarchical technique might be able to deal with that. Okay, I've got one more optical flow method for you. 3-for-1 deal today. This one is called Farnsbach's method, and this one's a little bit different in that it estimates the brightness using some sort of 2D polynomial function to compute the translation between frames. And this technique really is hierarchical, so it's using a pyramid that goes from coarse to fine. And to use this one, it's also very similar. It's just now we're going to use an optical flow Farnsbach object, okay? And you can say how many pyramid levels you want and how many iterations. And here, the flow vectors, they are also quite dilated compared to where the actual object is. But the vectors are maybe more precise in the sense that they're all pointing in a very similar direction. So let me run that one for you while we're here. Okay, here's a more complicated example. So here we have 2 frames from a video sequence, and you've got cars going in every which way. I personally would not want to drive in this intersection, but I'm a cautious driver. Anyways, the task for optical flow is to determine which way the vehicles are moving. And if we run, Farnsbach's method on this, here's what we get. And here it's done, I think, a really nice job of telling you which direction those cars are moving. It's even computing optical flow fields for these people. that are kind of walking. So now you have maybe a good appreciation for where objects are moving in this video clip. And thanks to optical flow, we have a way to reason about it. Okay, so you can use optical flow in the ways I've described. And in fact, optical flow has a lot of really cool uses. Here's an example for frame interpolation. So the idea here is that you've got a video sequence, and the video sequence is at kind of a slow frame rate, okay? And you want to increase the frame rate to make the motion higher, smoother motion, but you want to avoid any artifacts, okay? And the standard way to do this is to do frame blending, where if you have current frame, you want to get to the next frame, you kind of like interpolate between the two frames. So basically you insert a bunch of intermediate frames and then just kind of interpolate through time. That gets you a certain amount of quality, but with optical flow you can do better. And let me play you a clip. So on the left is the original frame, original video. In the middle, we're doing this frame blending technique. So we're kind of interpolating between two frames of time. And on the right, we're using optical flow, essentially to warp the image based on the flow field. And as we slow the frame rate down, you'll see you get a lot of artifacts using frame blending. But with optical flow, there are artifacts if you look carefully, but it looks much more natural. And it's quite a nice effect. See that? Okay, so what I'd like to do now is an exercise. And the task is to try to match a camera motion with the optical flow field it produces. So, if you've got a camera in a scene, okay, and you start moving it, maybe you're translating it, maybe you're rotating it in different ways, which way are the pixels going to move in the image? So the task here is to match a letter, A through F, with a number, 1 through 5. So why don't you take a minute or two, and then we'll work it out together. Feel free to talk it out with a friend nearby.
Same
still working on it, but in the interest of time, let's see what we've got. So, so A is rotation around this x-axis, so the camera's kind of going like that. What kind of optical flow field do you think it produces? 1, 2, 3, 4, 5. 2. Right. Okay. So as the camera's going up, the pixels in the video are going down. Okay. What about B? What do you have? 1. Yeah, that's right. So the camera's going right, pixels are going left. What about C? 2. Yep, that's right. What about D? 5. Yeah. So this type of flow, actually, it's this point here is called the focus of contraction because the flow field is like contracting at the singularity. You can imagine if the camera's going forward, this flow field's going in the opposite direction. It's called the focus of expansion, just in case you're curious. Okay, 2 left. What about E? 3. Yep. And F? 4. Yeah, there you go. Okay, great. So why don't we take a break for 10 minutes, and when we get back, we're going to talk about tracking. All Grab your seats, please. We're going to get going again. Okay, so before the breaks, we were talking about motion estimation, and we got into optical flow, trying to figure out where pixels are moving. And in fact, what I'd like to do in the second part of today's lecture is talk about tracking. And in fact, there are lots of ways to implement tracking, lots of algorithms. We're going to focus on feature point tracking. And the idea here is to find very important points, like distinctive points, and then track them through time through a video sequence. So this is a little bit different than optical flow. In optical flow, you want to compute these motion vectors for every pixel. But in this problem, we're only going to find a small number of points to track. And we want points that are very reliable. And as mentioned earlier, these tracking type problems are a little bit easier when the motion is small. But even if we have small motion and we're trying to deal with a small number of robust points, there's still a lot of challenges here. First of all, we need to figure out what are good features to track. We want to do it efficiently, okay? So we want to maybe do this in real time if possible. We need to be able to deal with changing appearances, like spectral highlights and shadows. We want to avoid drift, which is accumulating error. We might have to deal with occlusion and disocclusion, where things become hidden or unhidden in the video sequence. And points might get lost because they've gone out of the field of view or they become occluded. So there are a lot of challenges to deal with. Okay, so to get started, it helps to think about what makes for a good feature. If you want to find really good features to track, what does that mean exactly? Well, a good feature should be distinctive, okay? So you want that feature to be easily identifiable in the image in the next frame, okay? You don't want it to suffer from the aperture problem. Okay, we saw before, the aperture problem can cause some issues about perceived motion. And we want that point to be consistent through time, that feature to be consistent through time. So let's think about edges for a second. Let's say I have an edge at time t, okay? And then I have another edge at time t+1. This actually isn't such a good feature to track because we've got the aperture problem, as we described earlier. So what else can we try? What about homogeneous regions? Here maybe I have like a region that's white or blue. Well, that's not so good to track either because it's not distinctive. We touched on that earlier when we were talking about optical flow. What about corners? Corners are good, okay, because corners are distinctive, okay? They don't suffer from the aperture problem, and they can be consistent through the video as long as you have similar conditions on each frame. Okay, so the point of this slide is corners are good for tracking. Okay, so if we want to track corners, first we need to find corners, and in fact, you've already learned about corner detection. So corners are a specific type of feature point. They're distinctive, they don't suffer from the aperture problem. And we can actually implement corner detectors, which are going to look for changes in intensity in two perpendicular directions in the neighborhood around the pixel. Okay? So here, for example, I have this region here denoted with the blue square. This is not a corner, and it's not a good feature to track because actually, if you think about it, the derivative of the image intensity along x is small. In fact, it's 0 if we're talking about a pure color image here. Same thing in y, okay? So both of these derivatives are very small. What about on the edge? So on the edge, if I take a derivative along the horizontal axis, actually I do have a very large derivative because there's a big change as I go from sort of black color to a white color. But that's only along the x-axis. Along the y-axis, actually things aren't changing. The corner actually can be found where both of these derivatives are high. So if I take a derivative along x, there's a large change, and same thing along y. So we can find corners based on derivatives. But this kind of approach, it's good, but it's not perfect because actually some of our corners might be, might not be axis aligned. Okay, so if I have, say, this rotated square, now my corners, you can see them, but they're not axis aligned. So what we want to do instead is find a rotation invariant way to find corners. And for that, we can actually take a look at the eigenvalues of the structure tensor. You're probably wondering, what is the structure tensor? The structure tensor is a matrix. It's a 2x2 matrix, and it encodes the local derivatives around a pixel computed in a patch. Okay? So around a pixel, I grab a patch. Okay? I can blur that patch using a Gaussian kernel. You know how to do that. Then what I can do is I can put these derivatives together. Okay? So here I have derivative in x, and that's squared. And over here I have derivative in y, that's squared. And then in these off-diagonal elements, I have the product of the horizontal derivative and the vertical derivative. Okay? So this thing is called the structure tensor, and it basically encodes the gradient in the neighborhood around a pixel. So you can actually write your own code to compute the structure tensor. It's not hard because you learned how to do image filtering and how to take derivatives of images a few lectures ago. Here I'm going to load an image. I'm going to blur it using a Gaussian filter. Okay. Now I'm computing derivatives with respect to the x direction and the y direction. Okay. And I'm using filter to apply this derivative kernel. And you've done this before a few lectures ago. Then what I'm doing is I'm putting these elements together that go into the structure tensor, okay? And then I'm applying a Gaussian filter. And here's what the different elements in the structure tensor actually look like. Okay, so to find the corners, what we need to do is do an eigenanalysis of the structure tensor. And essentially what it does is it represents the structure tensor in terms of a rotation matrix, okay? And that's going to encode the orientation of the edge. And then we've got these eigenvalues, which encode the strength of the gradient along the edges, where the edges might have been rotated. Okay? So the orientation of the edges, they're the eigenvectors, and the eigenvalues are going to be based on the strength of the gradient along those directions. So we can encode the eigenvalues so that the first one is bigger than the second one. And since the structure tensor is a symmetric matrix, these eigenvalues are always positive. Okay, it's just part of the mathematics. Okay, so in MATLAB, you can do this. It's really easy. You can use this function called SVD, okay, singular value decomposition. And here, S is the structure tensor. And what comes out of here is three matrices, U, D, and V. So D is going to have the eigenvalues along the diagonal, okay, and that's what you see here, 3 and 1. And then U and V are going to store the eigenvectors, which encode the orientation of the edges. So the way I think about this stuff, I think about it intuitively using ellipses, okay? So you can think of an ellipse that is going to be aligned based on the prominent edge. So maybe here I've got a strong edge that's going in this direction, okay? And that's encoded by this vector here, negative 0.7071 and positive 0.7071. Okay, that's kind of going in this direction. And then I can scale that vector based on the eigen value. Okay, so this vector has a length 3. And then in the orthogonal direction, okay, I've got a vector that has a length 1. And if I draw an ellipse around those vectors, then this is a convenient way to think about the eigenspace comprised of the eigenvectors and the eigenvalues. Okay. So why is this useful? Well, again, we're talking about finding corners. And this actually gives us a very convenient way to find a corner for structures that are maybe not axis aligned. So I can find corners on rotated objects. So if both my eigenvalues are large, then I have a corner. If I have one eigenvalue that's large and the other one's small, it's an edge. And if both eigenvalues are small, I'm in a homogeneous region. And that's kind of depicted in this plot. Okay, so here's my homogeneous region. Both my eigenvalues are small. So if I draw this, I get something that looks like a kind of small circle. Here I've got an edge, and one eigenvalue is very large, okay, and it's pointing in the direction of the edge, right? The other eigenvalue is very small, so I get kind of an elongated ellipse. Here, on the corner, I have two large eigenvectors, or two large eigenvalues, sorry, and the eigenvectors are orthogonal. So here I have a corner. So here I have a way to compute corners that are not on axis-aligned objects. Does that make sense? Okay, so we can use this to find corners. And in fact, since both the eigenvalues are positive, you can actually look at the smaller of the two eigenvalues, because both of the eigenvalues when you have a corner should be large. So if the smaller one is large enough, then you can say you have a corner. And in fact, this was the concept of a paper that was written in 1994 by Shi and Tomasi. And their paper was called Good Features to Track. And the way they found good features to track was they looked at this eigenvalue. If it was big enough, then they've got a point that they want to track through a video sequence. Here what I'm doing is I've got an image. It's kind of a synthetic image I made in Microsoft Paint. Okay, and then I computed the eigenvalues, and here I'm showing the second eigenvalue. And hopefully you can see it's got a strong response at points that really do correspond to corners. Okay, so this thing actually works. Okay, so if you want to, you can be like me. You can write your own code to compute eigenvalues. But if you're a little more, taking advantage of MATLAB, you can just use this function called detect min eigenfeatures. And this does the heavy lifting for you. So here you pass in the image, okay, and then it's got some optional parameters, and it will give you points in the image that have a strong response based on this eigenanalysis. So you can configure the size of the region of interest in order to look for corners. There's also this Gaussian standard deviation. You can set that, and you can have some filtering to remove erroneous corners. And if you do that, it will pick up a bunch of good corners for you. It might be hard to see in the back, but there are a bunch of red dots on this image. Maybe the people in the front you can see. So this is what the detect min eigenfeatures method found for this image. Make sense? Okay, so we have a good way to find corners, and in fact, you also learned about the Harris corner detector a few lectures ago. That's also very related. Here, Harris is talking about a cornerness function, which is also based on eigenvalues. Okay, and in fact, you can compute corners this way as well. It's very similar, and you also here's the cornerness response image. You can see it also picks up corners even if I have objects that are rotating. So in MATLAB, there's also, oh, sorry, question?
Is that picking up curves in this?
Well, you don't want it to, but yeah, it might. Like here, for example, it's picking up this curve as a corner. But arguably, this is a corner, right? It's like a rounded corner. So it's not a bad result. And you know, maybe by controlling the parameters in the function, you can maybe make the window smaller so that it doesn't respond as strong to those kind of round corners. Okay, so in MATLAB, you can use this function called detect hairs features, and it will find you know, corners for you. And yeah, similar story. So you can control the region of interest. So you can say how big the window should be. You can control the filter size, etc. So just kind of in a similar way, you can find corners. So we've got two ways now to find corners in an image. Okay, so what I'd like to do now is talk about how you can use the Canade-Lucas-Tomasi tracker to track these corners through a video sequence. So we call this the KLT tracker because Canade-Lucas-Tomasi is a bit of a mouthful. But those are 3 computer vision scientists who invented this technique. In fact, this is a very popular method, and what it's going to do, it's going to track those corners through the video sequence as long as they you know, have a consistent appearance and they stay within the field of view. So the way this thing works is it uses the Canade-Lucas optical flow method. Okay, we talked about that before the break. And it's also going to apply that to a sparse set of points. In fact, these corner points we just talked about. So this method in MATLAB, actually, it's got some additional features which I think are pretty cool. So the first feature is bidirectional error calculation. The idea here is that if you have a point on the current frame, t, okay, if you can track it into the next frame, okay, let's call it t plus 1, actually, if you reverse time, you should be able to take that point and track it back to the original point, okay? But if there's some sort of error, okay, we're not going to end up at the exact same location, and we can encode that error and try to minimize it, okay? So essentially, what this technique does is it looks at the error, and if that error is too high, then it assumes that the point is lost. It went out of field of view. Another thing this technique does is it uses image pyramids, and we touched on those earlier. Essentially, this is a scale space technique that uses the image that's been downsampled to multiple resolutions. So at the base of the pyramid, I have the original image, okay, this original resolution. And then at this next level, the pyramid, I've got the image, maybe it's been downsampled by a factor of 2 in width and height, and so on. So I can construct this pyramid of images. And the way this works is we're going to run the KLT algorithm in a course-defined fashion. So we're going to start off running the tracker on these low-resolution frames, and then we're going to project them onto the higher resolution frames, and so on. And this helps you deal with large displacements. And you can do this on both frames, okay? If you've got a video sequence, you can do it on frame t plus 1, and you can then you know, iterate to get the full solution. The other things you can control are the neighborhood size, so how big of a neighborhood you're using to compute the tracker, and the number of iterations. Okay, so anyways, when you put all that stuff together, in MATLAB there's this method, it's actually a system object called Vision Point Tracker. And it allows you to track these set of points from one frame to the next. So in order to use this, you're going to create a point tracker system object. Then you're going to initialize the tracking based on some points identified in the first frame. Okay? And maybe for that, you're going to run a corner detector. So you find these points, then you're going to feed them into this point tracker system object, and you call the step method It's going to step the tracker, so it's going to find where those points went to on the next frame. And then you can go back and possibly add new points if some points were lost, like maybe they went out of the field of view. You can bring in some new points, maybe using a corner detector on the current frame. Okay, so here's an example actually with a face. In fact, it's my face. So what I've got here is a video I captured from my webcam. Okay, this is me in my office. And first thing I did, okay, I did a face detector, okay, and then I drew a rectangle around my face. I think you all are probably experts at this now, based on the coursework. Okay, so now what we want to do is find some good features to track through the video sequence. And what I'm going to do is I'm going to call the detect min eigenfeatures method, okay? And it's going to find points all over the image that you know, are corners. But if you notice carefully, what I've done is I've also constrained it to my face. So I've given a region of interest, which is the yellow box. I've told it only give me corners in the yellow box. So I've got that, and here I'm visualizing all the points that have been detected. Okay, so it's found all these corners. Some of the corners are, I think, quite interesting. Some of them may be not so interesting, but nonetheless, I've got a bunch of corners. And now what I want to do is track those points through the video. So what I'm going to do is I'm going to create a vision point tracker system object, okay, and I'm going to initialize it with the points that are in my face. Okay. So that's what you see there. And then what we're going to do is we're going to loop over all of the frames of the video. Okay, so this is exactly what we saw in the first part of the lecture. We're going to grab the current frame, okay, I, and then we're going to step the point tracker using the current frame. And essentially what this is going to do, it's going to take all the points and figure out where they moved into the next frame using the LKT tracker. Then for the points that are still in the field of view, then I'm going to visualize them. And here I'm drawing them as a white dot, a white plus symbol, and then I'm updating the points. Okay? And that's about it. So I'm going to go through this whole video sequence, and when I'm done, then I'm just going to release the point tracker. So as I move my head around the points, they kind of track my face, okay? Some of them get lost. So you see here some of the points, actually they got kind of fused on some of the books that were in my office. But most of them are tracking my face as I'm moving my head left and right, going towards the camera. Okay, we can take it further. So if I've got these points, then what I can do actually is I can fit a bounding box around my head. And as my head rotates, I can rotate the bounding box. So here, what I'm going to do is I'm going to get a bounding box around my head. And then as the points are tracked, what I'm going to do is use this estimate geometric transform. And I'm going to use a similarity transform to transform the points based on their motion. Okay? So I've got all these points on, say, the current frame. Then when I get to the next frame, the points have moved. Okay? What I'm going to do is compute the rotation and the translation, which maps these set of points to these set of points. Okay? And in fact, we did these things back, I think, in lecture 2 when you learned about you know, similarity transforms, projective transforms, how to warp one image into another. I think you did that in lab 2. This is basically the same thing. Here, though, the transformation is more simple. It's just a rotation and a translation. Okay, so anyways, once I can compute that transformation, okay, then it's represented by X form here. I can then apply the transformation to the bounding box. And what I get is a bounding box that's rotating with my head as my head rotates. And it also scales, okay? So as I get closer to the camera, the box gets bigger. As I move away from the camera, it gets smaller. So this is kind of a cool example of using a point tracker along with some of the other things you've learned about in this module to do kind of a cool effect. Does that make sense? Any questions? Yeah.
Is deep learning used in this context?
Yeah, you can definitely use deep learning in this context. We're not doing it here, so this is all sort of classic computer vision. But yeah, you can definitely do deep learning for these things. And in fact, next week's lecture is all about deep learning. But I don't think I'm going to cover this specifically. But with deep learning, you could say build a face detector. You can also actually do this KLT tracker. There are people working on that with deep learning. So yeah, you can use deep learning for pretty much all of this.
You have like a spherical shape you're trying to track instead. How effective is your detection?
Yeah, probably not that effective if the brightness on the object is very smooth. So, the corner detector, it wants, strong derivatives in two directions. And if you have like a spherical object that has very subtle gradient on it because, it's very smooth surface, then corner detector probably isn't going to work well. So, there are limitations to this approach for that type of application. Yeah.
Is the phase tracking system affected by how conveniently you rotate the phase?
Well, yeah. So if you have a lot of motion, or especially with motion blur, some of these points might get confused. And in fact, well, it's hard to see it here, but on the previous frame, we saw some of the points that get lost. But as long as you have a good number of points that are being tracked effectively, then you can always use ransack or some other technique to estimate this transformation, even in the presence of outliers. Question here?
How do you account for those points that go AWOL? So,
Yeah.
and make sure they're not included in the transformation?
Yeah.
If that makes sense.
Yeah, so you can, so you can keep track of the points. Like some points are going to become lost. Okay, they've gone AWOL. Maybe they've gone off the field of view. Okay, so they're no longer visible. What you can do actually, in fact, you need to do this, is to keep track of the points that are still visible. So if it's gone off the field of view, then you need to update that, and that's what we're doing here with the point tracker. We're telling it, these are the points I see on the current frame, so that when we go and step the point tracker on the next frame, it's not going to use any of the points that were lost. So that's how you deal with points that get lost.
Yeah.
What's not happening here, though, are adding new points. So what you could do is, where the face is inside this bounding box, you could rerun the corner detector on the current frame, and then you could pick up some more points. You just want to probably make sure that the points you're picking up aren't the same points you had already, right? But yeah, so that's a way in which you can add points, and then this gives you a mechanism to deal with the points that were lost.
And what about the points that started tracking books?
Yeah.
So yeah, because they're no longer in the rectangle with
Yeah, so you could filter them out.
Okay.
Yeah. But even if you have outlier points that are still in the rectangle, you can use ransack to estimate this transformation. So,
Yeah.
so this transformation, it's a very simple model. It's a rotation and translation. So it's 2D, so it's 3 parameters. So we have a simple model to fit to a bunch of points and with outliers. And so you can use ransack to do that. Yeah. Okay, any other questions about this one? Okay, so with these kinds of techniques, you can do all sorts of cool stuff. And a couple of years ago in this module, one of the things we had students do was combine a point tracker with augmented reality. So sort of putting concepts from this lecture together with concepts from the last lecture. And the way this worked was we actually used the tracker to track points in the video. But these were very special points. So we actually tracked the eyes and the nose and the mouth. And we made some simple geometric assumptions in 3D about those points. Like the separation between the eyes is 60 millimeters and so on. And essentially we created a 3-dimensional coordinate system on the face. And then those 3D points, they projected to 2D. We tracked those points using the 2D tracker. and then we were able to estimate a transformation, which allowed us to project a 3D object into the video clip. Okay, so here I've got a fake mustache that's on my face, and as my face turns, the mustache follows my face in kind of a realistic way. We also had other things like hats and sunglasses and stuff. So, you know, it's kind of a fun thing to do. And using the techniques you've learned about in this module, you can do this. Okay, so we've covered sort of motion detection and optical flow, and we even talked about point tracking. I want to talk about a few other things with video before we wrap up and give you some time to fill out the forms. So another really interesting topic in video is action recognition. So here it's kind of like image classification. So in image classification, maybe you have an image and you want to classify it into one of 10, maybe 100, maybe 1,000 different classes, okay, like ImageNet. But here what you want to do is you're given a video sequence and you want to put it into, in this case, one of 10 actions, okay? So I've got a video, this person is jumping, okay? And we want to be able to classify that action into one of these categories. And in fact, there's been some really interesting work on this. So this was the Weitzman action data set in 2007. It had 10 different actions. So you can try to do this classification. And you can imagine there are lots of ways you could approach that problem. You know, you can compute motion fields like vector fields of optical flow and feed those into classifiers, etc. But that was over 10 years ago. These days we're in the era of big data and capital competitions. And this one's actually super interesting. This just happened in 2018, just a couple months ago. There's the YouTube 8 Million Challenge. And this was at the European Conference on Computer Vision. There was this challenge where you're given access to 8 million YouTube videos, which is just a ridiculous amount of data. It's 450,000 hours of video. And you have a vocabulary of 4,716 classes. So what you want to do is classify the video into one or more of those classes. So for example, here are videos of people playing guitar, okay? So if you're given a video sequence and you know you've got someone playing a guitar, you want to give it a guitar label. But maybe there are some other labels that you want to associate with it, like you know, musician or you know other things. So every video can have multiple labels. So this just happened, and the winner was not surprisingly using deep learning. They had a convolutional and a recurrent neural network to deal with this kind of data. But yeah, interesting things you could do. You can imagine how useful this would be. There's so much unstructured content on YouTube or other video channels on the internet. You know, how do you organize that data in a convenient way? So this gives you one way to do it. Another really interesting topic in video is video description. And when I first saw this, I was blown away. So what you're trying to do in this task is to take a video and then produce some text explaining what's happening in the video. So you can imagine this is a pretty challenging problem. But here are some examples, okay? So here's a video clip of a dog that's swimming in a pool, okay? And the ground truth really is a dog swimming in a pool. And these people built a network, okay? And the network involves a convolutional neural network to look at the video data. Then they have a recurrent network to deal with the text. And their network predicted a dog is swimming, which is pretty good, I gotta say. You know, and that's just from the images. Here are some more examples. You know, somebody's like cooking, okay? The ground truth, a woman dips a shrimp in batter. It's really specific. Their network predicted a woman is cooking, which, you know, is really fantastic. So, you know, this was a paper that came out a couple of years ago. People have also been working on this. There's been subsequent research in this field trying to describe videos purely based on the video content itself. Okay, another really cool application is emotion detection. And this gets into a field known as affective computing, where you want to understand how people are sort of interacting with technology, what their emotional state is, etc. And you can do these kind of things where you can identify face, but not only that, you identify maybe the eyes, the lips, the lip contour, the eyebrows, etc. And then try to understand sort of the emotional state of the person. Are they happy? Are they sad? Are they frustrated? Etc. And there's a bunch of research being done in this area, also based on videos. Okay,